Example 4 wants us to evaluate cosine of alpha minus beta, where cosine of alpha is equal to negative 12 over 13, with alpha in quadrant 2, and tangent of beta equaling 6 over 5, with beta in quadrant 1. So let's first use our sum and difference identity to rewrite cosine of alpha minus beta as cosine, cosine, sine, sine. So cosine of alpha, cosine of beta, and cosine has the opposite sign. So we're going to put plus sine of alpha times sine of beta. So now that we have that down, we can fill in some of the values. So cosine of alpha is already given to us as negative 12 over 13. And that is the only one that's given to us. So the other values we will need to figure out. So I'm going to draw a right triangle, and actually alpha is in quadrant 2. So let me redraw this. So I have my angle alpha here, and I know that cosine is negative 12 over 13, and cosine is, if I follow SOHCAHTOA, adjacent over hypotenuse. So the hypotenuse will be 13, and the adjacent side length, although it's not a length, or although lengths cannot be negative because it's on the left side of the y-axis, I'm going to put a negative 12 there to represent the x-coordinate of the terminal point. And now we want to figure out, I'll just call that y. And so I'm going to use the Pythagorean theorem to figure out what y is. So we have y squared plus negative 12 squared is equal to 13 squared. So we find that y is equal to 5. And now that's going to help us because we need to find sine of alpha, which is opposite over hypotenuse. So that is going to be 5 over 13. And now I'm going to do the same thing, except I'm going to do it for beta. All right, so I know beta is in quadrant 1 this time. So there's my angle beta, and we know tangent is opposite over adjacent, so this is going to be 6, this will be 5, and I'm going to label the hypotenuse C, and we want to figure out 6 squared plus 5 squared is equal to C squared, and we get 36 plus 25 is equal to C squared, and so we get C is equal to the square root of, let's see, 1, carry the 1, so 61. Okay, so the length of the hypotenuse is equal to the square root of 61, and so that's going to tell us that cosine of beta is adjacent over hypotenuse, so that's going to be 5 over square root of 61. And sine would be opposite over hypotenuse, so that's going to be 6 over the square root of 61. Okay, so if we do some multiplication now, if we multiply these together, that's going to give me negative 60 over 13 times the square root of 61. And then this, if we multiply together, gives us 30 over 13 times the square root of 61. Luckily, both of those things have the same denominator, so we can combine them into negative 30 over 13 times the square root of 61. And normally we don't want to have a square root in the denominator, so I can multiply this by the square root of 61 over the square root of 61 to rationalize the denominator, and that is going to give us negative 30 times the square root of 61 over 13 times 61, And then lastly, we can multiply 13 and 61 in the denominator to get negative 30 times the square root of 61 over 793. Example 5 says, find the exact value of sine inverse of 2/3 plus tangent inverse of 4. Now, I think something that's going to be helpful for us is both of these things inside the parentheses represent angles. And so I'm going to call this angle alpha, and I'm going to call this angle beta, so that we kind of have a similar thing happening as we did in example 4. So I'm going to rewrite this as sine of alpha plus beta, so that I can then use the sum and difference formula for sine. Now, if you don't remember, for sine, it's sine, cosine, cosine, sine. And sine starts with s, so we have same sign, so we're going to put plus, and then sine of beta. Oh, that's not right. It's sine, cosine, cosine, sine. So then cosine of alpha times sine of beta. Okay, so now I'm going to come over here, and we know that sine inverse of 2/3 is equal to alpha. And if we apply sine on both sides, or if we think about rewriting this so that it doesn't contain the inverse, this is the same thing as saying sine of alpha is equal to 2/3. And then we know that tan inverse of 4 is equal to some angle beta, and that is an equivalent statement to saying tangent of beta is equal to 4. And it might be helpful to think about it as 4 over 1. So I'm going to draw my right triangle. Here's my angle alpha. And I know that opposite over hypotenuse is 2 over 3. And if I call this b, then we know that b squared plus 2 squared is equal to 3 squared. And so if we solve that, we get b is equal to the square root of 5. Okay, so similarly, here's my angle beta. I know that tangent is opposite over adjacent, and so we need to figure out the length of the hypotenuse. So we get 1 squared plus 4 squared is equal to c squared, and we'll get c is equal to the square root of 17. Okay, so let's go ahead and fill in these values. Sine of alpha we know from here, so that's going to be 2/3 times cosine of beta. So cosine is adjacent over hypotenuse, so that's going to be 1 over the square root of 17 plus cosine of alpha is adjacent over hypotenuse, so that's going to be square root of 5 over 3 times sine of beta, which is so opposite over hypotenuse. And now if we multiply, we get 2 over the 3 times the square root of 17 plus 4 square root 5 over 3 square root of 17. And we can combine that to be 2 plus 4 root 5 over 3 root 17. And then if we wanted, we could rationalize the denominator. And if we do that, we get the square root of 17 times 2 plus 4 root 5 over 3 times 17, which is the same thing as 51. And our final answer does not look so pretty, but that is the exact value of the thing that we were asked to evaluate and simplify.